Hey friends.
What's up?
I think we have the microphone figured out now, so you might be able to hear us better than last video. Sorry it took us so long to learn that. But we're learning about the nature of EM waves.
Okay, so an EM wave is a little bit different than the other types of waves that you guys have been learning about. And that's because it actually consists of two fields, okay?
Whoa.
So there's an electric field and then there's a magnetic field. And they move in opposite directions of each other to combine to make an EM wave. So you basically have one going up and down and one going side to side, okay? So snakes and roller coasters together.
Ooh, I like that. I think use that for regular kids. All right, producing the EM wave. It's not something you go in the kitchen and make yourself, but if you could, first you'll start with a charged particle with an electric field.
So think back to static electricity when we talked about particles being charged.
Like negatively charged, positively charged. So it's going to have a field regardless. Now, as that particle moves, it creates a magnetic field.
Wah, wah.
Remember we did that with the electromagnet? We took electricity and we made a magnet. This is what's going on with light. And it's called electromagnetic waves. So you see the electro part and the magnetic part. Pop it all together, you get a wave.
Like a compound word.
Okay, so that the wave itself is called a wave, but the wave carries energy. That energy isn't called energy because that'd be way too easy. We call it radiation. So electromagnetic radiation is an energy that is transferred through the space by the EM wave.
And the cool thing about EM waves is they do not have to have a medium. So they can travel through completely empty space, and we're going to give you some proof of this a little bit later in our presentation.
Waves are
Zoom.
fast, like really fast. That's your kilometers per second. What is that in miles per hour? Put her on the spot.
Yeah, tricky.
It's the speed of light. An EM wave, a light wave, the light we see is a type of EM wave. So EM waves travel at the speed of light because it is light. And that's, if you want to know the speed of light, you can just like rattle that out and you'll sound super smart.
Okay, so there's basically two theories that have been developed to explain EM waves. Now keep in mind, theories do not mean that they are in fact the absolute truth. They are just two thoughts about how this spectrum works.
So you're saying we really don't know?
Absolutely.
Okay, we have two ideas.
But
no for show knowledge. Idea number one, wave. The EM waves are waves. I like that. So the theory is that the light travels as a transverse wave. Remember transverse here? Dun, 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 with crests and troughs. So light travels as a wave, which is what you heard of totally, like light waves. Here's your proof that light is a wave. We have this thing called polarized light. She's showing you a little filter there. Light passes through a polarizing filter in one direction. I said one direction. One direction, what? Okay, let me show you a picture before we show you the crazy stuff. Okay, if light is a wave, which it is sometimes, look at this green little light here. The light goes as a wave, crest trough, crest trough, crest trough, crest trough, crest trough. It can fit through the fence. But if we had a light going this way, sideways, crest trough, crest trough, crest trough, it can't fit through that fence anymore. It only can fit through the fence that's going up and down. Now, if light, I'm going to give you a little spoiler here, sorry. If light were little bitty particles, little bitty dots, it doesn't matter what way the fence is going, what way the light's going, a dot can fit through anything. A little bitty particle can fit through anything. So here's what Ms. Burkhart's going to show you in a second. And then there it is. Okay, so we have, no. Okay, we have those things right here. Kind of crazy expensive. So they have itty bitty slits going in different directions.
So you can see through one polarized filter.
Ooh, it looks
Can you
darker.
see us?
So
Okay.
why does it look darker?
It looks darker because it's blocking half of the light. So you're decreasing the wave by using one polarized filter.
What happens when you use two?
Well, this is what you want to happen with your sunglasses.
Wear my
You want
sunglasses.
polarized filters, two of them, so it blocks all the light.
Then we won't see where we're going.
Well, that's true. I guess you want just one.
You just want one.
Okay. If you want to see where you're going, I guess you only want one. But if you want to risk it, you want two. Okay? So all the light is being blocked, so you shouldn't be able to see us through it. Okay?
Put it real close.
Now, you might be able to see the reflection of the camera, but the camera is on the computer, so you're not actually seeing through the filter.
We can't see a preview ourselves, sorry.
Right.
So if you look here, this one has slits going horizontal, this one has slits going vertical. That blocks 100% light, because at this point in the middle, all the light's only going horizontally. So if you put a polarized filter that's going this way, they can't fit.
So the horizontal filter would be a picture of representative when you have what's called polarized sunglasses.
And here, they can use them for cameras too, you photogs out there. Look at this left side of the screen. Whoa. It looks much more clear. They put a polarizing filter on the lens of the camera, and it blocks half the light, which gets rid of all the icky reflections if you see on the right side of the screen. There's no photoshopping at all. It's just polarized filter versus unpolarized filter. Okay, but light's not always a wave.
This is where things get tricky.
Oh, we already did that.
Okay, so the other theory is that light isn't a wave, it's individual particles that travel in a stream. Okay, so like little tiny pieces that together make up the stream of light.
You might have heard of photons before. And also, this is where we get some root words like photograph and photoelectric effect.
And photosynthesis.
Oh, yeah, good one. 10 points for Gryffindor.
What?
Okay, so here's some proof that light is not a wave, even though we just proved it, but this is proof that light is a particle. So you have the photoelectric effect. Thank you, Einstein. Like literally, he came up with this. It says that it knocks electrons out of a substance when light is shined on it. So here's a solar panel that you will be using soon. Don't know if you can see it. But the solar panel, like, it's inside the plastic case, there's a little piece of metal here. And that metal is stock full of electrons. Kind of like a cup that has, like, filled up 100%. And as soon as you add one more drop of Wawa, it all spills over or starts spilling over. So that's what's happening here. This is 100% full. As soon as you start letting more light hit it, all the particles are absorbed, and it starts spilling out the electrons in the wires, causing electricity. Get photons, electricity, effect. I know, right? So here's what you see, a little graphic. You see the light hitting the electrons and are forced out, and they cause a current. That's a little ammeter there, which measures current.
And something that you guys have a lot of experience with that actually uses the photoelectric effect is calculators that have solar panels up at the top, which is how they turn on and off. They don't have any batteries.
Well, this one doesn't have a battery, so if I cover it up, the numbers go away. This is a cheapo.
And we also have solar panels on the roof of our building because we are trying to become more green, and without having to use electricity, we can take it from the sun and put giant ones of these on our roof.
That would have been a good assignment. Did I think about that?
For them to build one?
No, for them to, like,
Oh.
investigate. Okay, kids. I think that's it. Oh, yeah, we already did that. So that's it. If you have any questions, come see us because this stuff is a little confusing. We expect you to understand the two different ways that light behaves, and that is, it's very confusing. So if you want to have a conversation with us, come find us, and we will clarify everything. We'll shine some light on the subject.
We didn't talk about, though, how we know that electromagnetic waves don't need a medium.
Oh,
Is
no,
that later?
We should talk about that real quick.
Okay, so here's your proof that electromagnetic, unlike mechanical waves, do not need a medium to travel through, is that there are electromagnetic waves that actually travel through space because light is an electromagnetic wave and we receive light from the sun. And so if it couldn't travel through open space, if it had to have a medium, we would not get any light from the sun.
No sunlight. We're just no bueno.
We would be in big trouble.
Yep. Okay, kids. Enjoy the rest of your time.
Hasta la vista,
baby.